Exercise 2E, using graphs to solve equations and inequations. We're just looking at now absolute value equations and inequations and solving those graphically. So first thing, part A, we're just going to draw the graph of y equals the absolute value of 2x minus 5. Just going to do that here. Now, okay, just got to be careful there. So I'm just going to do up a little table of values. So when x is 0, I get 0 minus 5, that's negative 5, absolute value of negative 5 is 5. When x is 1, I get 2 minus 5, that's negative 3, absolute value of negative 3 is 3. When x is 2, I get 4 minus 5, negative 1, absolute value of that is 1. Now I'm just going to leave a gap, okay? What I want to do actually, I'm going to leave a gap. I'm going to do when x is 3 and I get 6 minus 5 is 1. Now we know that this is a V-shaped curve. So we know that that is a V-shape because it's an absolute value graph, but you really want to find where it's, so I've got 1, 2, 3, 4, 5. And when x is 1, y is 3. When x is 0, y is 5. When x is 2, y is 1. I also know that when x is 3, y is 1, and when x is 4, if I do 4, when x is 4, I get 3. So 4, 3. So what would really be good to do here is to find out what the x-intercept is. So x-intercept, we're going to sub y is 0, and we get 0 equals the absolute value of 2x minus 5. So let's just solve 2x minus 5 is 0. And we get that x is 5 on 2, or 2.5. So when x is 2.5, and if you put that in there, 2 times 2.5 is 5, minus 5 is 0. We get that y is 0. So here, the graph actually looks like this. Okay, so just be careful. It is not x minus 5. If it was x minus 5, it would be shifted over to 5 here. But it's not, it's 2x minus 5. So really what we need to be doing is seeing what value of x makes this 0, okay? We've got, obviously these are two different straight lines, and this one has a positive gradient, and this line has a negative gradient. And here it says write down the equations of the right hand and left hand branches. Now if I look at y equals absolute value of 2x minus 5, for any values of x, we can see here that the critical point, or the x-intercept, is 2.5. So if I look at any values greater than 2.5, say like 3, 4, 5, etc. So when I look at 3, x is 3, I get y is 1. When x is 4, y is 3. If you go larger values, you'll always get a positive value of y. So what we've got is for x greater than 2.5, or greater than or equal to 2.5, the equation of the line is just y equals 2x minus 5. We can see that it's the positive gradient, okay? So just writing that up there, y equals 2x minus 5. Now, if we look here, when x is 2, for example, I get 2 times 2 is 4, minus 5 is negative 1. But then you take the absolute value of it. So how do we go from negative 1 to being, for example, positive 1? Because the absolute value of negative 1 is 1. But what we're really doing is taking the negative of negative 1. So when I'm getting negative 1, I need to take the negative of negative 1 to give me positive 1. So where you've got, where what's happening in the absolute value sign, if you do get a negative, for it then to become a positive answer, like what we've got here, you need to put another negative in front of it. Okay, so for example, when x is 1, 2 times 1 is 2, minus 5 is negative 3. How does the negative 3 become a positive 3? We take the negative of negative 3, and it becomes positive 3. So, and same with 0. 2 times 0 is 0, minus 5 is negative 5. The negative of negative 5 is 5. That's how we take the absolute value. So therefore, if we want to write this equation with no absolute value sign, okay, see, when you write it with the absolute value, it gives you the V shape. If I just want, for example, this branch here, it would be, that's the positive gradient one, is just y equals 2x minus 5. So I want this version of the line, it's the one with the negative gradient. But we know for values of x less than or equal to 2.5, you always, or less than 2.5, you're always going to get a negative value in here. So to take the absolute value, you do the negative of the negative. So if I take the absolute value signs away, I write y equals the negative of all of that. So negative bracket 2x minus 5, which is expanding the bracket now, y equals negative 2x plus 5. So that's the equation of this branch, and it makes sense. Negative gradient cuts the y-intercept at 5. Okay, now, right, sorry, I've already put another graph there. So this is part C. Sorry, I've worked ahead a bit. It says on the same diagram, draw the graph of y equals x plus 2. Just done a little table of values there. And you can see the graph here when x is 0, y is 2. When x is 2, y is 4. When x is 4, y is 6. And then I've extended it along. You can see that the graph, the black graph, y equals absolute value of 2x minus 5, and the light blue graph intersect at 2 points, P, and I'll call that one Q. So to find the points of intersection, if you want to find the point of intersection P, you have to solve the light blue line, y equals x plus 2, with this line going in this direction, with the negative gradient line, so with y equals negative 2x plus 5. So to find point P, as I said, this one here, it's the negative gradient of the absolute value bit with the x plus 2 graph. So we're solving y equals negative 2x plus 5 with y equals x plus 2, solving those simultaneously. And you put sub 1 into 2, and you'll get x plus 2 equals negative 2x plus 5. Taking the 2x over, bringing the 2 over, you'll end up getting x is 1. Right, so when x is 1, sub that up here, you get y is 3. So point P is the point 1, 3. Makes sense. Point P is the point 1, 3. Now for point Q, you use the positive branch of the absolute value function with y equals x plus 2. So the positive branch is y equals 2x minus 5 and y equals x plus 2, solving them simultaneously. You can sub 1 into 2 and you will get 2x minus 5 equals x plus 2. So we get 2x minus x equals 2 plus 5. We get that x is 7. That looks about right. And when x is 7, we can see here that y would be 9. So point Q would be the point 7, 9. And let's have a look. And that looks fine. Q, 4, 5, 6, 7 looks about right. It's the point 7, 9. Okay. Now for part E. Therefore, if you're asked to solve absolute value of 2x minus 5 equals x plus 2, what it's really asking is for the x values of the points of intersection. So we're looking at the x values only at the point of intersection of the graphs y equals absolute value of 2x minus 5 and y equals x plus 2. Now we've already done that in part D, and that is the x, these are the x values of points P and Q. So therefore x is, and if we look at our answers, we had x is 1, then we had x is 7. So these are the solutions. So if you want to solve that, you get x is 1 and 7. And if you just substitute, you can check it. When x is 1, on the left-hand side, you get 2 minus 5, negative 3, absolute value of negative 3 is 3, and 1 plus 2 is 3. They equal each other, and 7. On the right-hand side, you get 9, and on this side, you get 14 minus 5 is 9. Absolute value of 9 is 9, so yes, they are solutions. However, now that we know the points of intersection and the x values of the points of intersections, you can be asked things like this to solve absolute value of 2x minus 5 is greater than or equal to x plus 2. So this is asking you, where is the y equals absolute value of 2x minus 5 graph? This would be above the line y equals x plus 2. And you've done these before in other questions. Let's just put the graph here so we can see. So where is the absolute value graph above the light blue graph? Well, here's the absolute value graph. It's above here for values of x less than 1. Okay, so it actually, at x equals 1, it's actually the point of intersection. So you would not say, oh no, it's greater than or equal to. Yes, so we can say the solutions are x is less than or equal to 1. And we know that this is the 0.79. So for values of x bigger than 7, like up here, okay, as we go more across here, the absolute value graph is above the other graph, and it would be x is greater than or equal to 7. Okay. All right, and that's how you do those. So the important thing here is to write, for the points of intersection, to write the equations of the two branches by putting a positive in front of your absolute value sign for this branch, and then doing a negative in front of the absolute value sign when you remove it for the other branch to get your two equations. Exercise 2E, question 14D, sketch the equations below and find their points of intersection. So we've got y equals absolute value of x minus 1 and y equals 2x plus 2. Might draw the graph of y equals 2x plus 2 first, all right? Right, so when x is 0, y is 2. When x is 1, we get 4. When x is 2, we get 6. When x is 3, we get 8. And when x is 4, we get 10 up there. Okay, so we've got this 2x plus 2 is a fairly steep line. And when x is negative 1, you get 0. So this is the line y equals 2x plus 2. Now that's they've got a gradient of 2, okay? Then we want to look at drawing the line y equals the absolute value of x minus 1. So looking at that one, say when x is 0, you get negative 1. When x is 1, you get 1 minus 1 is 0. When x is 2, you get 1. So we've got 2, 1, 1, 0, negative 1. Now, you should recognize this as just y equals absolute value of x, and then the whole thing's shifted down 1 unit. So instead of being here, it's shifted down 1 unit. Also, when x is negative 1, absolute value of negative 1 is 1, 1 minus 1 is 0. And negative 2, absolute value of negative 2 is 2, 2 minus 1 is 2. So we can just put some of those in. Okay, so it looks like this and like this. Now, so this is the curve. The whole thing is the graph, so I'm not going to write it there. The whole thing is the graph of y equals absolute value of x minus 1. Now, if I draw the equation, I want to write the equation of this section. Now, this section has the positive gradient, so this would just be y equals x minus 1. And this side, so if you look at when x is negative 1, negative 2, you have to take the absolute value of x there. So this equation would be y equals the negative of whatever x is, because, so this is for values of x less than or equal to 0. This equation is for values of x greater than or equal to 0. Because I can see here the v occurs when x is 0. So this is the positive branch, that's the negative gradient branch. So when x is positive, this x value just stays positive. So when x is 1, it's 1. When x is 2, it's 2. So you may as well just write it without the absolute value sign because it doesn't change. But for negative values of x, right, so when x is negative 1, you've got to do negative negative 1. So you take the negative of the x and then we just write the minus 1. So that is the equation of this branch here. And it does look right. It's got a gradient of negative 1 and it cuts at negative 1. And this has a gradient of positive 1 and it cuts at negative 1. Now, we have to find the points of intersection. Now, so let's look at this. Let's look at this first point of intersection. Look, I can see that actually the point of intersection is negative 1, 0, but you could solve simultaneously to do that. But if I did a table of values here for this graph, when say x is negative 1, I get 2 times -1 is -2 plus 2 is 0. I can already see the point of intersection is -1, 0. Okay, so this point of intersection is -1, 0. But let's say you didn't see that, you would solve simultaneously. And what would you solve simultaneously? You'd solve the negative branch of this absolute value function. So you would solve y equals -x minus 1 with this graph, with y equals 2x plus 2. So we're solving those simultaneously. You would just put them equal to each other. So 2x plus 2 equals -x minus 1. And just solving that, you get 2x plus x equals -1 minus 2. I've got that 3x is -3, so x is -1, and that's what we have here. Okay, so the point of intersection when x is -1, if you sub into any of these, you would get y is 0. So the point of intersection is -1, 0. That's your point of intersection. Now, if this line up here has a gradient of 2x, and this flat line here has a gradient of x, they are never ever going to meet. Okay, now, how can we show that algebraically? So let's say we solve y equals 2x plus 2 with this branch, y equals x minus 1. If they never meet, it would mean that we would never get a solution here. So let's see if that works. So solving simultaneously, we've got 2x plus 2 equals x minus 1, and I've got 2x minus x equals -1 minus 2, and I've got x is -3. Now, the thing is, x is -3 is down here. What that solution is if this line was continued. Now remember, this equation of y equals x minus 1 is only for values of x greater than or equal to 0. So because my answer is not greater than or equal to 0, this is not a solution, since x has to be greater than or equal to 0. What that is the solution of is, if this was continued, this is where the line y equals 2x plus 2 would intersect with the normal line y equals x minus 1. But the thing is, we've got the absolute value function. So this is why this is the equation of the line only for values of x greater than or equal to 0. And this, y equals -x minus 1, is only the equation of the line for x less than or equal to 0. So if I look at my point of intersection here, I did get -1, which is less than or equal to 0. So it fits in that domain. Whereas my answer here of x is -3 does not fit there, which is why it doesn't make sense on the graph. Okay, so therefore there is only one point of intersection. Okay, and then, for example, in question 15D, you are then asked to solve the inequality. So now solve the following: absolute value of x is greater than 2x plus 3, and you look at that and you look at these and you say, but they don't look right. So let's just have a look what that is. So remember, if I put these equal to each other, and I'll just do that down here, but this is what we've got. We had y equals absolute value of x minus 1, and we had y equals 2x plus 2. So if I put them equal to each other, absolute value of x minus 1 equals 2x plus 2, and if I just take this x over, the 1 over, sorry, I get 2x plus 2 plus 1, which is plus 3. This is actually the same as the two that I sketched. So whatever the solution was for these two equations, it'll also be the solution for y equals absolute value of x and y equals 2x plus 3. It'll give me the same solution. So if I want to solve that, the points of intersection are just the same. Okay, so where is the absolute value function higher up than the straight line? So where does that occur? It occurs here for values of x less than or equal to -1. Look, so the solution would be x is less than or equal to -1. Now, I know that's a bit tricky. What you may also be asked, and probably most times you will be asked the following, is you'd be asked to solve absolute value of x minus 1 is, I think this is meant to be greater than, oh no, it was just greater than, is greater than 2x plus 2. So if I asked you this, absolute value of x minus 1 is greater than 2x plus 2. They're the two graphs that you've drawn, right? So if I was solving this, if I take that 1 over, you can see that the solution to this is just the solution of what you did, okay, which is x is less than or equal to -1, because you read that from the graph, okay? So that's your solution. Okay, now this one's a little bit trickier. You've got a parabola with an absolute value function. So it says to sketch y equals x squared minus 2 and y equals absolute value of x. Now we know that x squared minus 2 is just the x squared curve shifted down 2 units, okay? So I might just plot some points. So when x is 1, I get -1. And when x is 2, I get 4 minus 2 is 2. Okay, it would look like that. And when x is -1, I think I get -1. And when x is -2, I would get +2. So this is what it looks like. So this is y equals x squared minus 2. And y equals, so this was the point, I think it was the point 2, 2, wasn't it? When x is 2, I get 4 minus 2 is 2, so that's 2, 2. And this one was -2, 2. Now, if I sketch y equals the absolute value of x, so when x is 0, y is 0, when x is 1, y is 1, when x is 2, y is 2, you can already see a point of intersection. And when x is -1, I get +1. And when x is -2, absolute value of -2 is +2. Oh, I can see the other point of intersection. Now, we can actually see, just by graphing, we could read off the solutions, okay? And my solutions are, so according to this, where do these two curves cut? They cut when x is 2, so the graphs intersect when x equals over here -2 and 2. So therefore they are the solutions of x squared minus 2 equals absolute value of x. But if you were to solve it like we have been doing in previous questions, and let's say you did not choose the values I chose to sketch and you could not see that they were the points of intersection, if this is y is absolute value of x, so when x is positive, the graph is just y equals x, and when x is negative, this is just the graph y equals -x. So I've got the two branches. So if I want to find this point of intersection, or this one, let's call this P and let's call this one Q. So to find P, you have to solve y equals -x with y equals x squared minus 2. So it's the parabola with y equals -x. Be very careful, because that line -x is also going to cut down here, but I only want the solutions. This is just, you only want solutions for negative values of x, okay? So therefore, to solve those, I would put the two equations equal to each other and take everything over to the left. And I would factorize, and I would get x plus 2, x minus 1. And my solutions are x is -2 and 1. But x has to be less than or equal to 0. Therefore, x is -2 is my solution. Okay? X equals 1 is not a solution. So x cannot equal 1 in this case. And you can see that that other solution would be down here, but our line's not going down there. And then to find point Q, that's the positive branch of the absolute value function, which is y equals x. You would solve that with y equals x squared minus 2, putting those two equal to each other. X squared minus 2 equals x, taking everything over to the left, putting it equal to 0 and factorizing you would get x minus 2x plus 1. So therefore you get x is 2 or negative 1. But for point Q, we're using the positive branch. So we're only looking at values of x greater than or equal to 0 here for this. So therefore x equals 2. X cannot equal negative 1. This is since x is greater than or equal to 0. So there's my two solutions. X is negative 2 and x is 2. You just got to be careful with those. The reason there are two solutions here, 2 and negative 1, there's your 2. And if I extended this line, there's your negative 1. So yes, the line y equals x does cut the parabola twice, but we only are allowed to do values of x that are positive, okay, for this second one. And to find p, we only want values of x that are negative. We're not interested in this other solution if I continued the line there, okay? So now, finally, I can then ask you, hence solve x squared minus 2 is greater than the absolute value of x. So it's asking me where is the parabola above the absolute value function. And we can see that that would be for values of x less than negative 2 and values of x greater than 2. So the solution is x is less than negative 2 and x is greater than 2. Okay? One that's slightly different. So sketch y equals 2 to the power of x and the line y equals negative 1, and then hence explain why 2 to the power of x, this inequation, is less than or equal to negative 1, has no solutions. Okay? So we'll just do that. Okay, so we're sketching y equals 2 to the power of x. So when x is 0, y is 1. When x is 1, y is 2. And we know that the curve looks like this. This is y equals 2 to the power of x. You know, when x is negative 1, you get a half, and so on. Now I'm going to sketch the line y equals negative 1. Now, this is saying, so 2 to the x is less than or equal to negative 1. Is the graph 2 to the power of x ever below the line y equals negative 1? Well, it's not. So this has no solutions since 2 to the power of x is always greater than 0. Its y values are always greater than 0. Therefore, it's never going to be less than or equal to 1. However, but 2 to the power of x is greater than or equal to negative 1, if I was asking that. So this one has no solutions, but if you were asked to solve 2 to the power of x is greater than or equal to negative 1, this has solutions, all real x. Since for every single value of x, this is since the curve y equals 2 to the x is greater than 0 for all real x. So if it's greater than 0, it's going to be obviously greater than negative 1, okay?